So I'm going to quickly talk about voltage division, how we use it, derive it, and go over some examples using voltage division in real problems. So firstly, we use voltage division when we have multiple different impedances or resistances connected in series, meaning they're connected just directly head to tail, you can think of it, head to tail, or you realize that in this mesh, the current going through these impedances, resistances, is all the same. So that makes these connections here, this entire circuit, a series circuit, meaning that the voltage across each one of these resistances is going to be different. So we're going to have a voltage across resistor 1, voltage across resistor 2, and voltage across resistor 3 that aren't going to be the same unless all of those resistor values are equal to each other. So voltage, the voltage division rule helps us figure out how much voltage is across this resistor, the voltage across this resistor, and the voltage across this resistor. But first, we need to simplify our circuit down to something that looks like this circuit down here. This circuit down here can help us derive the voltage division rule. It's not a particularly difficult equation, but it's good to help visualize where it's coming from. So we know from Ohm's law that the current I1 going through this mesh is defined by I equals V over R, where this V here is our source voltage source, and our R is our total resistance of the circuit. So this being a series circuit, R1 and R2 are in series. So this R is going to be R1 plus R2. So we can rewrite that as V over R1 plus R2. So then we also know for looking at voltage division, we want to find the voltage at a specific point. So to find the voltage across R2, so if you were measuring plus to minus here across R2, will be our output voltage. Let's say V out. Our output voltage would be defined as Vs out is equal to Vs minus the voltage across R1. So you see that as the current drops, the voltage potential will drop from Vs to V out. So, and that drop is caused by the current going through R1. So we can say our I from up here, we can rewrite that as V R1 plus R2 R1. So this term here is our current, and this is our resistance, so voltage minus voltage. And then we can rearrange this a little bit. Sorry, this is also Vs. V out equals pull the Vs out completely. 1 minus R1, R1 plus R2. Do some simplification here. So you multiply these bottoms and then cross multiply. Yeah, cross multiply those. You'll be left with V out to Vs R2 R1 plus R2. So this is our general voltage division equation, in which we're going to use to solve our example problems here. So it's important to note that when we're given a more complicated circuit, we can simplify something like this down to something like this, where we have two resistances, R1 and R2. So I'll call R2 the second resistor of the combination, and R1 the first resistor of the combination. So going down to our first example, you have this example here. We're solving using voltage division, and we want to find this node voltage here is our V out. And just to label the rest of our nodes, this node here, we already know is Vs. And we can just label this VA because that node is going to be important. So first, we need to simplify this part of the circuit down here to look like this circuit here, so we can do our first set of voltage division. So R3 and R4 are in series. They have the same current flowing through them. So we can simplify our circuit to look like this. Everything else stays the same, except we just add R3 and R4 together. So we have, and I'm going to start writing the values just to keep track of stuff. We have R1 being 3 kilo ohms, R2 being 2 kilo ohms, and R3 plus R4, 3 kilo ohms. So now we have, in our reference, so now we have this 3 kilo ohm resistor in parallel with this 2 kilo ohm resistor. So another quick simplification, I'll just copy this over, and then this will simplify. We can either do product over sum, or however you want to do the math for this. Product over sum will be 3 times 2 over 3 plus 2, obviously. .2 kilo ohms. And then, so now we're left with, now this circuit leaves us here with something like we had up top. So now we can do our voltage division using our equation here to find what is effectively this no voltage here is still VA from our original circuit up here. So VA is equal to R2 in this situation here is our 1.2 kilo ohm combination. 1.2 over 3 plus 1.2, and this is all multiplied by our source voltage, Vs, which is 10 volts, gives us 1.2, 3 plus 1.2, 2.85 volts. So that's what VA is. So now we can come back up to our original circuit. Now we know what VA is. We have another voltage division problem. So I'll just label this voltage here 2.85 right there. So now this 2.85 volts is then being divided again by R3 and R4. So we can use our equation again. So just to directly solve for V out, 2.85. R4 was 1 kilo ohm. R3 was 2, I believe. Yeah. 2K plus 1K. So that means our V out is 2.85. 1 over 2 plus 1. 0.95 volts, or 950 millivolts as our final answer for V out. And then we can quickly confirm this just using LT Spice, because it's always good to double check the answers. Come in here and make a quick little schematic, and then run a DC operating point simulation. Our component values. One was 3K. Add our ground node, because it won't like if we don't do that. Operating point, and I like to just click off of this and then annotate the nodes. So now we see that our values were correct. We got 950 millivolts from our calculations and 2.857 for this is what we were calling node A, VA. So that intermediate step is very important.